when a trion decays, it also produces an electron. So that actually complicates. So the process photon decaying to exciton decaying to photon and trion decaying to photon is a little bit different. And because of this momentum restriction, they are actually in the absorption, it is the intensity or the contrast in the absorption curve is very low.
And in the PL, because you're pumping it with lots and lots of light,
right.
Then you will get some.
So although you will not be able to see it, but it is there, but it is not so much visible as it is visible in PL. So the absorption signature of the trion is very faint in case of this charged exciton.
And these are, I guess, these are not your data, but these are the low temperature ones.
These are low temperature ones. Yes. Okay. Huh?
Which material is
this? This is MOSC2. Sorry, I forgot to mention the material. So this is molybdenum diselenide. Okay. So now, so next thing that we are going to discuss is that what we will do with these two-dimensional exciton gas. So we'll put it in the microcavity, right? So these are the material that we use. So any TMDC material can be, we can basically think of using MOS2 and WSC2, MOSC2 and WS2, but different materials have different line widths. So depending on what wavelength regime you are interested in, you basically choose any material, right? And also depending on the cleanliness or the very narrow line width, you can basically choose. So for example, MOSC2 will have very sharp line width compared to MOS2, because in case of MOSC2, the defect density will be less than the other materials. So in our project, we basically have chosen MOSC2 for this experiment. And as we have already mentioned, so this has these properties. And next, what we will do is we'll put this material, we'll embed this material inside the cavity, and then so it's basically we'll study what will happen, and basically we'll study this. We'll discuss more about this curve, how we what these are meaning, and so this is the aim for the few slides. And now we basically, this is a problem of coupled oscillator. So we have two mass that are coupled by this spring in between, and we can basically think the same physics in when we are discussing this exciton which are inside the cavity. So this is, we can think about, this is a, so if I because we also have trions, so instead of two coupled oscillator, you can think about three mass that are connected together. So now we have three coupled oscillator problem. And so this kind of problem, if it is a coupled oscillator, we solved it in classical mechanics by, you can basically think about a matrix, and you diagonalize it, and you get the normal modes for the two coupled for this coupled oscillator problem. And as you know that the omega 1 and omega 2, the frequency, resonance frequency of each of these individual oscillator will basically change, right? So if for example, if this has, both of them has omega naught frequency, resonance frequency, and they were interacting, then they will resonate at different frequencies. So the difference between this omega 1 and omega 2 is basically in our case we call it a Rabi splitting. And so the same problem, we basically now think about this exciton inside a cavity, and now we describe this problem in terms of Hamiltonian, where we have the cavity photon. Now another thing that I forgot to mention is that we are talking about the cavity photon in the plane of the cavity. So this is a k parallel. So the photon is basically confined in between two distributed Bragg mirrors, and in the plane it is so you can think about infinite continuum. That is basically, it has a translational symmetry in the plane of the cavity, but you're basically confining in the vertical direction. So k parallel is basically, we are talking, so we can talk about this the cavity resonance at different k parallel, and then we have these lowering and raising operators for this photon and the excitons, and the coupling term that we include here is this G naught. And then you can write this Hamiltonian in 2 cross 2 matrix, and then diagonalize, and you get when you diagonalize, you get two modes, two normal modes, which are this alpha and beta, which we call in this case we call polaritons, right. So here, so this is a way of this framework to look at this problem was developed in 1958, and this model of this light matter coupling, where you basically model this exciton and photon Hamiltonian in this way, was first proposed by Hopfield, and so this model is basically well known as Hopfield model. And if I write down, if I basically get the normal modes, the energy, two different energy modes, will basically, it will depend on the k parallel, and we plot. So there will be two curves which will depend on k parallel value, and it is one curve will basically, we'll call it upper polariton branch, and the lower curve we call it a lower polariton branch. And now we can excite this system at signing at different resonance point along the curve, and the idea is that you can generate more polaritons in the lowest energy possible at around k parallel equal to 0. And if you have sufficient lifetime of this material, of these exciton polaritons, and also if they thermalize, they can actually form this condensation. But interesting thing is that even they are not at thermal equilibrium. People actually have done this experiment not in this TMDC, but using quantum well heterostructures. So, for example, gallium arsenide, gallium nitride, and aluminum gallium arsenide quantum wells, and there you can create multiple quantum wells which are sandwiched between two distributed Bragg mirrors, and that quantum well can also host this 2-dimensional exciton, right. And there you can also have these polaritons, but the problem is the interesting thing about this system is that here you have the exciton binding energy which is 0.5 electron volt, and there the exciton binding energy is very low. For example, if you grow these quantum well heterostructures, there the exciton binding energy is the order of tens of milli electron volt. So you have to do these experiments at very low temperature. So here and also the other thing is that this Rabi splitting is also very large in this newly developed material, which is basically is around 30 milli electron volts or 40 milli electron volts. But in this case, so what have been seen earlier is that if you create this polariton gas, and so they actually show different kind of nonlinearity behavior, and one of the signature that they found from this experiment, that they actually produce some laser. It's called polariton laser. So that actually forms when you have this condensation, and that condensation, since it has a finite lifetime, it decays, and actually it decays, and those photon, if you measure, it has a property of laser.
I have a question about this diagram. So I always thought about this physics as that you want to have the bare cavity and bare exciton energies become degenerate at some case. So the way you have drawn the dashed line, the bare cavity and bare exciton
they are not touching.
They are not degenerate at all at any point.
Yes.
And
yeah, so this is called the detuning. So you can basically change this detuning, and you can basically tune this lower point of this bare cavity and this bare exciton at the same energy, or you can tune this energy difference to lower it so that this curve crosses somewhere at these 2 points.
Yeah.
So that, but you can basically you can get the same behavior. So that will basically depend where your anti-crossings is happening. So, here the crossing is happening right at k parallel equal to 0, but there are other situation when you basically cross the upper parabola and this flat line, which is the bare cavity and the bare exciton at different k parallel points. So, if I, for example, if it crosses at 2, then the anti-crossing will appear here. This basically the nature of this plot will change. Okay. Now, so now the interesting thing, why this material is able to show the condensation properties close to room temperature, whereas we know that if we use ultra cold atom systems, which is diluted ultra cold atoms, where you can basically get the condensation, but you have to do it, you have to basically laser cool the system to microkelvin temperature or even less, right. It is because the critical temperature that is required to achieve the BEC is 10 to the power 5 times less, sorry, the mass of these particles, these cold atoms, are basically are 10 to the power 5 times less than this polariton mass, more than this polariton mass, and the mass is basically determines this Tc, right. So, Tc is proportional to, inversely proportional to the mass. So, now if I increase, if I reduce the mass of these ultra cold atoms, then we can increase the Tc. The same thing here. Now, since this is a combined part of half light and half matter, right. So, this mass of these particles are actually 10 to the power 5 times less than the mass of an electron, right. And in case of in case of cold atoms, the atoms that you use, it's much larger than the mass of an electron, right. So, now you can think that you already increases the Tc by a factor of 10 to the power 5. So, it basically brings it back to closer to room temperature. So, this is the reason why this BEC in solid state system is was interesting, and it is basically this work was proposed during 1990s, where so this, I think this work, let me see. Okay, I think it is in the later slide, where people first have people have already demonstrated this polariton signature of this polariton condensation around 2002 in using quantum Well-Hatter structures. Now, so now we use this material even so this material has even better promise in terms of temperature, right, because it has a binding energy which is 0.55 eV. And in case of quantum Well-Hatter structures, you have the exciton binding energy is of the order of tens of or maybe hundreds of milli-electron volt at most. Okay, now the future proposal for this field was to realize this. For example, you can use this polariton condensation to make this superfluid, so to form a superfluid state, and then you can control these superfluid. You can basically do some transport experiment, or you can drag the superfluid by a electric field. So, these are the kind of experiment people have proposed. Suppose this is a microcavity, and then you connect the quantum Well-Hatter structure with leads, and then you pass current, or you basically apply an electric field, so that you can perform. So, basically it will also produce some kind of supercurrent in this material. So, these are the idea that are proposed recently using quantum Well-Hatter structure, not using this material, because so far people have not performed this experiment with large area sample. All the experiments that I am going to discuss now. So, this is the work that first was experimental work was done in quantum Well-Hatter structure in 1992, where they first demonstrated these exciton polaritons in microcavity. This is the experimental result, where this is the microcavity and this is the quantum Well-Hatter structure, and you can see the quantum well is basically lying inside this DBR. These are the splitting, and I think it's not shown here nicely. And this is the curve that they have obtained. And here, for example, this is the question that you were asking, that At 0 detuning, you have this anti-crossing here, and at detuning is increases, separation between these two modes increases. Okay. Now we use this new material, and in old cavity which was already done in 1990s, and then so this is the work. So when we started this work, this paper was already out, and this is the microcavity geometry, planar microcavity geometry was used by this group from City University and City College of New York, and they had these TMDC material inside this cavity, and what they do is they basically shine a light from top of this mirror, and they change the angle of this incidence, and they measure the reflectance. So this is a, suppose for example, this is reflected light. So they use a detector here and measure the spectrum, and then they produce this curve. So they basically vary the angle and measure the resonance energy, and they basically demonstrate a Rabi splitting energy of 46.3 electron volt. See how much time. Okay. Now, so this is another work in that direction, but here the cavity geometry is different. So here they have used an open cavity where you basically etched a part of the upper mirror, and then you have a planar cavity here, and then you change the distance between these two mirrors by piezoelectric voltage. So you use a piezoelectric and then you change the voltage to change this distance. So that basically you will basically change the detuning of the cavity resonance, and you get you basically produce these coupling between the exciton resonance. So the exciton resonance is the bare exciton resonance is flat, and so this is the line where you have the resonance of the cavity mode, and when it meets, when the detuning is 0, you get a splitting here, but you see that there is something mysterious happening with the trion resonance. It is basically not showing a splitting here, right.